Hello and welcome to Conversation Oasis, a weekly discussion program coming to you from Kasviskeidas, from the heart of Turku. You're listening to Radio Robin Hood, and tonight we have a kind of quiet night. We have only three of us here in our professional studio. It's me, your host, Ville, and owner of the place, Jalal, and tonight's special guest we have Ronald Lesker, or Lasker, how do you pronounce
Lesker.
it? Lasker. Welcome, you guys. And
Hello.
And tonight we're gonna go a bit spacey, so we're gonna talk about space and possibly galaxies and what inspires us about the space out there. Space is the place, as they say. I have myself personally worked a bit at Tuorla's planetarium, and I have done some tours around the observatorium in Tuorla, in Kaarina, and I'm always inspired, especially about the children's questions about space. When they ask questions, they have always the best questions. Like I have just told them that light is the fastest thing in the universe, and they say no, it isn't.
Okay.
Like there are black holes and you can go through them, and I have to be like, yeah, that's actually true, but like for now we think it's the fastest way to travel or move, but maybe in the future we don't know really. So children keep their mind open about it. But Jalal, you are making all kinds of
I wanted just to mention my colleague to keep it a little bit more quiet. He was making some noises from the other side of the restaurant. Yep. But you said that what inspires us, your work recently is quite great. I went to visit him in that observatory that you are working to, and he has a tour for people, for visitors, and it was quite interesting. The animation was quite interesting and is inspiring children and as well adults.
So you went to the tour as well?
Yeah.
Mm-hmm. Yeah. Jalal came to see a couple of shows. Just to specify for the listeners, planetarium is the place where you have projectors and movies about space that are projected on a dome-like screen. And but here I would like to ask you, Ronald. You are researching stuff related to space, and what inspired you in the first place to be curious about space? Was it in the childhood already, or do you have some specific event that got your interest to it, or can you track it down?
Yeah. So actually, there's two things that come to my mind: space and then astronomy. I think, curiously, I was first in touch a little bit with astronomy from a I would say a children's book. I'm from East Germany, and there was some shortcomings in that country, but I think some things were very good, that they had a very straightforward way of having books for children, young people, introducing science and technology in kind of simple language, but very rich still and very accurate in information. And there was this book, and I really, really liked it. It had all kind of stuff like, that we also know from nowadays. Where you see kind of the sun and the earth compared to it, so small. And but it was the book was called in German Lebenslauf der Sterne. I guess a good translation is the stars' course of life, and it was mostly dealing with that. And it was very informative and not written in an overly, I would say, not very illustrative, not like crazy stories, dragon eating the princess or whatever. But it was pretty much to the point, and I liked that. But still, it had a little bit of this comparison, this allusion. And it starts with these lines. You look at the stars at night, and and it seems to be perfectly still and unchangeable, and it presses us, maybe because of that also, because it seems so unmoved and such a point of reference for us, like the ultimate things are ultimately addressed in some sense, and I think that's also a valid point, because for us with our hectic lives, that's what it is. So then the book continues, the second line basically, but now let's switch on a time lapse, like in the movies. And then we will see a spectacular play in front of us. And some stars coming into existence, and other stars changing their color, and some stars growing and expanding and becoming really huge, and other stars then eventually also dying, some of them in spectacular explosions, and so on it goes. So that's the introduction to that book, and somehow that fascinated me, that if you switch on this time lapse, and then it would completely change. So that was astronomy, and then I was, I guess, like some 10 years old around that. And then later in high school, towards the last years, I guess I found several things interesting, but one of them was physics. So I also did some sort of the slightly higher course in physics and mathematics, and that led me to consider also physics as a degree at the university. And all the time I was not thinking about astronomy at all somehow anymore, and I was fascinated with quantum mechanics and the math and also other things, like psychology I'm curious about, and I thought at some point I care about computers, but then I found out I didn't really, and all these things came and go, and the physics was really there. And then somehow, and maybe inspired by that book also, there was one relatively small part about how the life of a star can end in a black hole, as you just mentioned it. And somehow that, and I guess I've read one or two popular books about general relativity, about Einstein's theory and its application, how remarkably successful it is, and born out of this elegant, simple idea. And it proved still today that like all these predictions are true at an incredible level of precision. So I studied physics, and I did mostly theoretical mathematical work on black holes in my physics degree. And then I thought, I'm not that good. I'm not that good of a theorist. And if I do astronomy, then I somehow remembered it, that black holes is part of astronomy, and astronomy has so many facets, so many sides to it. Because in the universe, of course, all the physics is happening, and then I went for that. And but when you talk about space, that became really fascinating during my physics studies. So they are of course related a lot, or maybe even the same. But for me, it was the interest, this thinking about space and the fascination with what space means came with physics studies and general relativity mostly for me, and not from my childhood days so much.
May I put a question in front of you? If we look at that this way, that people who are seeking the truth, actually, they get interested either in philosophy or in metaphysics or physics or these kind of things. So you were, may I put it this way, that you were mostly trying to find the truth about...
That's actually a good point, I actually, when I was a teenager, I was a bit interested in philosophy, and unfortunately I stopped reading books on that. Like I rarely read a book nowadays. That has not to do with my work, I really have to admit, but I really liked always to philosophize with people, and that's actually a very good point. I think the truth, there's these two levels. There's the truth, but there's also specifically, I think, with these modern physical theories, quantum mechanics and general relativity, the fact that they are not intuitive to us, to our everyday intuition at least. So they do have undoubtedly philosophical impact, and that's another motivation. But I also found at the time, and still, the statements they make and the structure they have, and how you came to derive them, this sort of slightly crazy aspect that still, if you use the right language and if you go really step by step, if you do it strictly, you arrive at these seemingly crazy predictions, including traveling faster than light, maybe through a black hole, through logic, which is in this case encapsulated to a big part, at least in the math. It's not the only logic, but the math allows us to take several thoughts, which each of them we at least assume for a moment to be true, and then we can derive a new statement that is not obvious to us from just knowing that we have these three things that we know or we think we know. There's a way that this is always, whenever that happens, and still sometimes, fortunately, but unfortunately not that often, but sometimes still happens in my work, that I'm actually sitting down with a piece of paper and like writing it down and having my head heavy with something that, I try to do something, but how does it really work? And I can't see it. But then when you go step by step, you have to take that patience in a way. So really sit down, okay, I had it. Away with all that stuff. I'm starting from the beginning. I'm going step by step, and it works. It takes also some effort. It takes time, but you can get these statements, and then once you look at your solution or once you apply it, also nowadays also a bit easier. You have computers. You can plot things, visualize. So that helps. But it's not the way you arrive at the solution, not by visualizing things, which is what I criticize a little bit. In I would say the current culture in general, that just because you've been shown a representation, that's always what the picture is, that you think you've grasped the thing itself. So when you really go and you want to get something new, you don't just mix up different images. So the image is always a more or less restricted and possibly maybe even partially wrong or misleading representation. Now we could say the same thing about the math, which is true, but it's much closer to the truth, I guess.
I would say that
much of the images that we have in our heads. Basically.
This is interesting. I will talk about it, please.
I was just saying that how I've kind of thought about it is that most or some, at least quantum physics and some phenomena that we study about space are kind of in the borders of physics in a way that some of the theories are so that we need actually quite a bit of imagination to come up with a hypothesis, and there's the philosophy comes in a way. Of course it's built on data and things, but as you said, you have to take some assumptions and then some of these, and sometimes in the media, these theories come out as kind of very, how would I say, sexy articles, like for example, some scientist says that this, according to his possible crazy theory, it might be that for example, when they were trying to find the Higgs boson, the particle, that the Higgs boson prevents finding itself by traveling back in time, and sort of like making it disappear, the finding, so that the world doesn't end. This kind of things, like very story things, imaginative. But still, nobody could actually say that this is rubbish or anything, because actually the physics that we study, for example, what happens in the black hole and what's beyond the black hole, that kind of things. They kind of are in the boundaries, but
that's true,
and that can be inspiring. But also, I still related to Higgs boson. I read that when it was discovered, there was first like a very long session of statistics to make it clear that this finding is actually true, that it is not a
or at least very, very probable, as you mentioned statistics.
Any
measurement you make usually has some.
That's a good point.
Some uncertainty, some error to it.
Yeah.
However, if you make enough measurements, enough observations, what is enough that we decide basically? But you set usually, hopefully in advance, some level that you need to reach to then at least earnestly discuss whether you have really in this case, discovered the Higgs boson.
Yeah.
That's true. Yeah. So some of the, also in astronomy, there is nothing is forever certain.
Yeah.
In physics, at least.
We are just in the beginning.
We are always in the beginning. We're always in the beginning, and as I think was it Newton, or I may be wrong. I don't otherwise particularly like Newton from the little that I've heard about him, but I think he said what we know is a drop, and what we do not know is an ocean. And he had just at the same time probably he said this while he has made some of the major discoveries and inventions of the Renaissance and of laid the foundations of modern day science, and that influences all of us, right? I mean, the fact that we're speaking to this microphone now and have this recorded, or having any lighting in here other than fire.
Yeah.
There's like this. So now this is maybe digressing a little bit. I recently came across an online article which was describing, in a way, or in this case, taking sides with the so-called science wars, where there was a book discussed or reviewed in this online article. I think it was called A 4,000 Year History of Science, which apparently, I didn't read the book, but the review was overall quite negative, saying that they kind of relativize everything and basically make huge omissions about major discoveries, and at the same time discussing at length or speculating at length about a lot of things that in the end people have maybe been thinking or writing down, but that have not entered or have not sustained, like they were not successful. So we are always changing. I think that's one of the misunderstandings with the theory. If we say Einstein's theory of relativity is a theory, so it's just a theory, yes it is. Anything that we have, and probably beyond science also, any statement you make even in everyday life is in some sense a personal impression or an opinion. And this goes back to philosophy. What can we even know anything sure, like even beyond physics? Like can I know that I'm here now with you talking? Is that just in my head in some sense? So there's all kind of questions like this, but the misunderstanding is a little bit that at least I would say ideally, and hopefully still nowadays, although there is science that this may change a little bit, physics or natural sciences in general, they are very honest, I think, and they call things a theory, even though they have at the moment no evidence to the contrary. It's still a theory.
It's good.
Until the day comes, whether it's tomorrow or in 1,000 years, where we get clear or sufficiently clear evidence to the contrary, and then that theory will be replaced by a better theory. But if a theory that we have makes very, very few assumptions on the one hand, and makes many and testably precise predictions, then it is a good theory, and then we work with it because it guides us better, at least at the moment, than a previous theory, and in fact it seems to work, because again, otherwise we wouldn't have all this technology. So we're at least closer to the truth, speaking about truth again, than we were, let's say, 500 years ago. So there is a progress, even though we should consider all possibilities in principle. We should even review all ideas that have existed all throughout history. They can never be as such bad. However, it would be too much work and confusion, I guess, for a person nowadays, if you want to move ahead now, to go back and check everything that has been done and apparently been rejected based on data many times over by our predecessors, by our colleagues that lived before. So we have to, in practice, restrict ourselves a little bit in order to make better progress. So, sorry, I was talking too long, but
no. Please.
Yeah, just a reminder to our listeners that we are listening to conversation Oasis, coming to you from Kasviskeidas, from the heart of Turku, and I have with me tonight Ronald Lasker and Jalal, the host of the place, and me, Ville. and we've been talking about space and what inspires about space, and also we went to kind of this basics of what we can actually know. And related to that, I would like to say that I think the definition of scientific information is something along the lines of most credible belief, current belief that we have, and it kind of consists that it might change, and it probably will change.
Yes.
And as you mentioned, just that sometimes we could actually go back and review stuff. I think that sometimes happens. Then something new is discovered, and then you review. And I would I'm gonna soon give you also, Jalal, some time to say something. But I would just to ask also Ronald that along your career of studying space, has there been any kind of these changes which happen when, say, a new telescope is launched and new kind of information is coming? Has there been kind of these well, maybe not paradigm changes, but kind of these new ways of actually seeing what's out there, which changes our point, or at least for me, I'm always like, for example, currently I'm inspired by the European extremely large telescope, which is on the works. I think the original schedule was that it would be actually ready during 2020 or something. I don't know what's the schedule now, but I've heard that they, for example, can measure atmospheres of exoplanets and maybe get some info from there. That's an example for me.
That would be like a breakthrough, like that you say. So actually, it's very curious you say that, because there is probably many of such examples, and I think we had very few major breakthroughs in the sense of like even close to the quantum mechanics invention of quantum mechanics or general relativity, which maybe we should get back to a little bit, talking about space. I myself neglected that a little bit, but I think one example comes to my mind immediately. I should know more of them, but one is that we were through the Hubble Space Telescope. There were many other things that were made possible by Hubble Space Telescope, but it had a significant increase in the resolution that we can have in an image. So or also when we take a spectrum, so if you measure a spectrum on the sky, what you do is, roughly speaking, if you have an image, you have a pixel, which is either red or green or blue, or somewhere in between, a mix of red, green, and blue. And if we take a spectrum, we just split up the colors of the light that reaches us in more fine increments, and that we call a spectrum. And we can do this nowadays actually for what's called integral field spectroscopy. We do this for an entire image. So each pixel has a whole spectrum taken. So we not only have 3 color information for that pixel, but thousands of colors. Okay. And that we can use, for example, to analyze the chemistry of stars.
That's another universe, I think.
So in the Hubble Space Telescope, however, so it had also a spectrograph on board and an imager, so we can both take images and we can take spectra. At that time, the spectrograph was what's called a slit spectrograph. So we do not get these spectra for an entire image on an area, but we get it along a line. And so what they were able to do with in the mid-90s, when the Hubble Space Telescope came online, they say in astronomy, we could now observe and measure the motions of stars, which we measure, in this case, not because the stars are moving on the screen. That would be way too slow on the time scale, so we'd have to go back like in a million years and take a picture again, and then we would maybe have seen the stars moving. However, they still had enough. So how we measure the motion, because the stars move partially either towards us or away from us, and that way, the spectrum of these stars, which we know how it should look like if the star is at rest with us, but if it moves away from us fast enough or towards us, that spectrum gets red shifted if it moves away and blue shifted if it moves towards us. So all the spectral features are the same, but they're just moved to a shorter wavelength in case of blue shift, or a longer wavelength in case of red shift. And this we could do before, but the Hubble Space Telescope had a spectrograph, and it had a very high spatial resolution, which meant that we could measure the motion of stars very close to the centers of galaxies, where for other reasons we already suspected black holes. So in each, at least major galaxy, like our Milky Way, there is, and I mean, we know that partially only now, but it was already strongly hypothesized at the time. Each major galaxy has this supermassive black hole at the center, defined to be a black hole of roughly 1 million or up to 10 billion solar masses. So that's about the largest black holes that we have discovered in the universe. So they weigh as much as 10 billion suns. But in order to measure that mass, how can you measure the mass of something? There's two things. One thing is you could try to move it. That's actually called inert mass. So if I try to move you, I want to accelerate you, the heavier you are, the more force I need in order to accelerate you at the same rate. But you also have another mass, which is the force that you exert on Earth, or Earth exerts on you. It's called the gravitational mass. The force of gravity is proportional to your mass. So if you're twice as heavy, the gravitational force that will be between you and Earth will be twice. And in fact, there is also gravitational force between us. It's just very, very weak, but it's there. And in fact, that's how they measured, and still measure today, the gravitational constant, which is a constant in Newton's equation originally. So there's two factors, the two masses. Mass Wille, mass Ronald, in the case of two, sorry, for Jalal for excluding you now. So two masses, it's easier that way. So two masses.
But I'm just thinking about
two
the
masses.
Listeners that this is very...
Okay. So how do? You measure mass through the gravitational attraction. And now this black hole has also mass and the stars around it. So the heavier the black hole is, the faster the stars have to move around it in order to stay on an orbit. And they are most of them at least are on an orbit. And now we could tell exactly which star, how far, because the gravitational force depends on distance also. So I need to be able to distinguish stars which are very close and those that are a bit further away and measure their speeds separately. And that the Hubble Space Telescope could do for the first time, roughly. I think maybe there's been some ground-based from another telescope. So Hubble Space Telescope opened the door to us to measure black hole masses, which directly through the gravitational effect. That was, for example, a breakthrough.
Yeah. That's a good example. How about you, Jalal? What inspires you about space? We don't have much time left for this episode, but we will have another part. But
whenever I had difficulties with the studying, and I wanted to escape away from studying, so I was creating my own mind about the universe, the stars, and things like that. And it's amazing world to escape to.
It's an inspiring thing.
So you were thinking about the universe, space as a way of at least mentally escaping from this world?
This is mostly relating to what I told you. It's mostly seeking the truth, and the seeking truth takes you to physics and the world around you and space and everything else. Naturally it takes you there, I think. So you have to wait, thinking about God and religion, and if that is not satisfying, you go another way, which is what you have studied and what do you know, and also imagining about the science, and you make your own science fiction probably.
There's very interesting things indeed, when you think about space is very large, but we don't know exactly, but at the moment we think it's expanding, right? And still it's not infinite, at least as the current consensus goes, but it's without boundaries. So all these things, you can do the math, but to think about it, think about how can you imagine something, and it's not just something. It's supposedly it's actually the very universe we live in. That is, it's not infinite. It doesn't have infinitely many galaxies and stars and all that. And the diameter or the size in principle is also limited. But if you start walking one direction, you never hit the wall. So it's very interesting to consider these possibilities. I think, or how information can travel. We talked about it before, right? So there's the speed of light, but then there's a quantum effect which is called entanglement. So it means that you can do this in an experiment. It's been shown on a small scale. It comes out of the theory also. That basically, if you have two particles that were born from one event, and you know these particles have to have certain properties connected. So this classic example is the spin. So similar, is really similar to spinning top or a sphere, like globus, whatever you have, that you're just spinning it. And there's two particles, and because you've born them from one particle with zero spin, so that if you make two particles out of it, they have to have opposite spin, because spin is preserved in any physical process. It's one of the big ground tenets. We talked about postulates that has never been violated, so we know about this. Spin is preserved in any process in nature. So, but on the other hand, information cannot travel faster than light.
Yeah.
Right. But if you have these two particles, what happens if you observe something here and you know about it? What about the spin of the other particle? Because in quantum mechanics, first, before you observe, there's actually what's called superposition of states. So you don't know for sure. There's only a probability that the spin will be either, in this case, there's simple example, only up or down. So you don't know this before you observe that particle. And the particle, before you observe that spin, it will actually behave as if it has both spins at the same time.
Yeah, it's the Schrödinger's cat thing.
Exactly the same thing. And but then you can actually, there is an effect, and we don't know what this means philosophically. This is one of the big discussions that follow quantum mechanics nowadays. Are we all entangled? So, if the universe was born from some more or less singular event, we don't know exactly, was it really just one point in space, or is it maybe it was just very small, but in any case it was very close together. Everything, all of us, everything was so close together, and maybe everything that's happening is still a display of this entanglement, so it's still happening, and we're in this quantum mechanical way still interacting with the other end of the universe. We don't know. I mean, maybe I'm saying something wrong here. There's already some more advanced physicists than I am, and then they would tell me, no, we know this cannot be true. But I think this is this has at least been a very interesting question.
Yeah, I have to say that I think we are out of time for this episode, but because our topic was space, space cannot be covered in one episode of conversation.
Let's continue next week.
Yeah. Until next week, we will continue with another episode of Conversation Oasis going to space. Thank you guys for discussing this.
Thanks for listening.